Okay, so we found that if we have an ergodic process, then we finally get something that we're interested in that we can actually look at the process and estimate the mean and the variance and so on and so forth. Now, for this to work, this process must, of course, be at least wide-sense stationary. If it wasn't, then we couldn't get a single mean. So this concept of averaging a bunch of samples to get a single mean just simply wouldn't apply. I also mentioned that we have this estimator for our variance and estimator for the autocorrelation, but that we would revisit them. It's time to do that now. We need to talk about types of estimators, and we're going to start with this concept of a minimum variance unbiased estimate of something. This is a concept that's actually going to come back multiple times during this course. So what does it mean to be minimum variance unbiased? We have to unpack that, and we'll do each one individually. To start with, an estimate of a quantity of a statistical parameter is unbiased if the expectation of the estimate is equal to the true value of the parameter. Like this. This says that while our estimate may have errors in it, we may have problems with our estimate, we know that on average our estimate is going to, on average, be the true value. Or in other words, the expected value of this estimate is going to be the true value. Okay, so what does it mean to be unbiased? Excuse me, I should have said minimum variance. So an estimate of a parameter is minimum variance if, and this shouldn't come as a surprise, the variance of our estimate. Remember, the estimate might be different every time, so we can now speak of this in terms of a statistical quantity. So while the estimate may yield a number, the estimate itself is going to be a random variable. So we want the variance of the estimate to be less than the variance of any other estimator that is also unbiased. So why is this a variance? As from up above, we have that the expected value is, in this case, theta. So we're having the difference between the random variable, which is our estimate, and theta, which is the mean of that estimate. And we want to make sure that it doesn't vary too much from that value. So let's give this a shot and see how, if any of these estimators up above in red are actually minimum varianced unbiased estimators. We'll start with the simple one. Actually, I think this is probably all we're going to do for now, but well, we'll see. So we have that mu hat of x is equal to 1 over L times the sum of L samples of x n, like so. So what is the mean of that? The expected value of mu hat of x is going to be 1 over the sum, n equals 0 to L minus 1, times the expected value of xn. And for a stationary process, or wide-sense stationary process, that's just going to be mu x 1 over L times mu x. And by the way, we use the abbreviation wide sense stationary as WSS because it gets to be tedious to write that all out. And so there we, yes indeed, have a unbiased estimator. Okay, so the next step is to discover whether or not this is a minimum variance estimator. We're going to skip this right now. We're going to come back to it a little bit later because this concept of proving that something is better than any other estimator means that we have to have some way of expressing what any other estimator is, or at least how any other estimator might be different from the one we've got. And we haven't yet introduced the concepts to do that. As a teaser, we're actually going to limit our discussion to, in general, estimators that are linear. So in that case, we would be trying to show that there's no other linear estimator of the mean that has higher variance. But we'll come back to this concept later in the class. However, while we are on the topic of unbiased estimators, we can evaluate the estimate of the variance and show that actually the one we have here isn't quite unbiased. So we'll move on to the next page because this is going to take just a little bit of work. Okay, so in order to come up with an estimate of the variance, I need to say something I probably should have mentioned before, and that is that we're going to need to assume that each sample is independent of all other samples. And this makes sense, otherwise we might run into the degenerate situation where, for example, the first x of 0, say, was purely random, and then x of 1 through infinity, all the subsequent values were actually just equal to that first value. Then it wouldn't matter how many values we averaged. We're not going to get any additional information. So in order for us to have an ergodic system, we need to ensure that we're getting new information. Well, we're going to carry that one step further, and we're going to make sure that each sample is independent of the other samples. What we really want is for the expected value of sigma squared of x minus sigma squared of our hat, our estimate, to be equal to 0. So this is a little bit of a long derivation, but we're going to go through it fairly quickly with the miracle of pausing the video and writing out equations to make it go faster. But I'm also going to simplify a few things to facilitate this. And that is, let's just start by finding this so that we don't have to carry through this extra sigma squared. The expected value of sigma x squared is just sigma x squared. So we'll go ahead and write this out, and that's going to be this expression. Now, remember we are working on this one here in the middle. So 1 over L times the sum of the squares, the difference between our samples and the mean. And so we have our sample values, and where we had our sample mean, I've put in the expression for it. The other thing I've done is, instead of using brackets for our index values, I'm just using subscripts just to keep this a little bit tighter. So when we expand this out, it's going to turn into a bit of an expression shown here. Okay, a few things to note. One, we've got a lot of indices going on here. We've got our k's, l's, and our m's, and expressed all these values. We are having we're going to be able to simplify things somewhat in that since we have assumed that our values are independent, that means that the expectation of a product is going to be the product of the expectations, and that's going to be really helpful. However, we still have a lot of expressions here, and so to keep track of things as we go, I'm just going to label them and treat them each in turn. So, starting with A, this is fairly straightforward. We want to find this. We have each of the values is independent, and we have an ergodic process. So we're going to use the fact that the variance is just equal to the expected value of x squared minus the mean squared. So we can take the mean over to the right side and it becomes plus. So now we have this nice expression in terms of things that we already know. Okay, B is going to be a little bit more complicated. So we have minus 2 over L, sum L equals 0. Whoops, do that in blue. Minus 2 over L. Okay, now the way to do this is actually to divide this up into two expressions. The first one is going to be when L is equal to K. When L is equal to K, we have the expected value of xk squared. And so that's going to be k squared. And then the rest of that sum is going to be when they're not equal. So in this case, we're going to sum from 0 to L minus 1, and L does not equal K. Well, in this case, if they're not equal, then they're independent. They have different distributions. And so we can divide this out into a product like that. Well, there'll be L minus 1 of these, and so this then simplifies as sigma x squared plus mu x squared. So we're doing the same thing that we did before for part A, because we have that same term. And now we have L minus 1 times mu x squared. And that comes from this second term. Okay, well, we're getting closer. We've got one more term to deal with, and that is term C. And it shouldn't come as too much of a surprise, but we're going to deal with this in much the same way we did the last term. So we have our sum over L and our sum over M. And now we're going to divide out, we're going to pull out when M is equal to L and when they're not equal, just as we did before. So we'll do essentially the same simplifications that we did before. We get 1 over L squared, and now we have a sum of L of these. So we're going to have L times our sigma x squared plus mu x squared, and we'll have L times, and the L factor comes from this sum right here. The L minus 1 comes from the inner sum, and then we have mu x squared in the same manner as before. And then this simplifies like that. So now we can combine all of these together into a single expression. And we're going to get 1 over L times the sum. We're back to our k sum of our three terms in that expression. So A, as you recall, was sigma squared plus mu x squared. And we're going to sum up L of those, it's a constant value, and divide that by L, giving us sigma x squared plus mu x squared. And with similar operations, we're now going to get minus, oops, that L should be an N, or N should be an L. There we go. Sigma x squared plus N times mu x squared. And when all is said and done, we can write that in terms of our final expression, which is L minus 1 over L times sigma x squared. So what does that tell us? Well, we were hoping that the expected value here would equal sigma x squared. And so that tells us that the true unbiased estimator is going to be different than what we just did. The unbiased estimator will be essentially L over L minus 1 times the estimator that we had. And the estimator that we had was 1 over L times the sum xk over k minus mu hat x squared, and that's going to be 1 over L minus 1, k equals 0, L minus 1. So this is actually a proof that you could, I'm sure, look up online. The point of going through this right now is that it illustrates some of the processes that we might go through when trying to prove things in the future. So this would be the unbiased estimator of variance. I'd like to take just one more minute and describe an important software programming implication of these things. So in MATLAB, we have the following functions and similar ones in Python. That is, the mean function of x gives our sample mean, just as we've seen it before. Variance gives the unbiased version of the variance, as we've seen that before, as we just finished developing. And variance with the parameter comma 1 gives the biased version of the variance. Now, the biased version of the variance and the unbiased version of the variance are essentially the same when you get large L. And the reason why we even care about this biased version is that it actually has a little bit lower variance in our variance estimate. In other words, while it's biased slightly, it's also not going to vary as much. So the last thing that we need to discuss is the cross-correlation function. We can use that to get the xcor function to give us the autocorrelation of x. Here's the problem. Suppose we have some samples of x. I'm not quite sure why it's giving me this problem. There we go. And pretend that those two waveforms are identical, the same thing. To get the autocorrelation, we take the signal, shift it relative to itself, take the product of all the terms that are lined up, and average them. Well, that type of operation works great for the mean, works great for the variance, but for the autocorrelation, as you can see, as we get further and further shifts in our autocorrelation, we have fewer and fewer terms that overlap. So if our original length is L, our overlap is now going to be potentially, much, much less, that's what I'm looking for, than L. That means the estimate of that autocorrelation term is going to be poor. So the impact of this is that the autocorrelation estimate for small lags or small values of M is going to be fairly reliable. But as we get to larger values of M, we're using fewer samples to calculate it, and it's going to get less reliable. So here's what that looks like in MATLAB. We have the autocorrelation of a white noise sequence here. So the correlation value should be 0, except at a lag of 0, where it should be 1. So in this particular sample, we have a sequence of length 400, and we see something that approximates the ideal. Like I say, it should be 1 right here and 0 everywhere else, and it's small, but it's not 0. What we actually get when we calculate using just the straightforward approach is that the wings, if you will, get much more noisy because we're using so few values to calculate those autocorrelations. So MATLAB has the biased autocorrelation that you can calculate, and the biased autocorrelation, it does the same operation in that it shifts and takes the product of corresponding terms, but then instead of dividing by the actual overlap, it divides by the full length, L. As a result, this is also not accurate. Neither of these are accurate. The biased correlation, which divides by 1 over L for every sample, ends up causing that to be very small because we maybe are adding 20 or 30 terms and then dividing by 400 in this particular case. So it's going to be small. It doesn't really represent the autocorrelation. On the other hand, if we multiply and sum 20 terms and divide by 20, it's so noisy that sometimes we get spurious large peaks. So you pick your poison, but it's good to know that both options exist, and whatever package you're looking at, you may want to double check for those. In order to do the biased autocorrelation, that is XCORR. Oh, I've got it written up above. I'm a biased.